Bending moments and shear force diagrams are fundamental for all structural engineers. It's something that allows you to understand structural mechanics. There's also some really important things that you can derive from them. Bending moments and shear force diagrams are really not that complex. It's all about just maintaining equilibrium. Because if you're not in equilibrium, you're obviously moving. And what structure, especially most structural engineers, are designing static structures. But before we start drawing them and deriving some of these key aspects, it's important that we understand some of the key basics of what loads are and what supports are, so we know how to derive them correctly. So now let's just start with the basics and understanding your loads. And we'll start with the most basic load, which is a point load. So as the name suggests, it's just the point that's applying a force to your structure. And this can be in any direction. So it could be pulling the beam up in shear, pulling the beam down in shear, pulling the beam across in tension, or back into compression. So even a column can have a single point load on the top that's applying a force trying to compress it. So there's nothing more complex than that. It's just a single point applying a force on your structure. So if we get to something a little bit more complex and something a little bit more common, that's a uniformly distributed load, or UDL for short. As the name suggests, it's uniformly distributed over a single area. So this can either be a single portion of your beam or for the whole beam. And this is where we're getting the simple calculations of like W. Typically that's the designation that you see in a lot of books. And this is just a uniformly distributed load of a fixed rate. So either 1 kilonewtons, 2 kilonewtons, or 3 kilonewtons, or even half a kilonewton. But it's uniformly distributed over a given length. These can be a little bit more complex because you can get variable distributed loads, or VDLs. As the name suggests, the load is still distributed, but it's variable. So at one end it's at 1 kilonewton, at the other end it can be half a kilonewton or 2 kilonewtons. But for this basic tutorial today, we'll just stick with point loads and UDLs, as they're really the easiest one. But there is one more load that we missed, and that is a concentrated moment. So that's either an in-plane twist, so you're trying to twist the beam around its primary axis, or torsion if you're trying to twist along it. So these are the type of loads that you can apply to a simple structure. But just beyond that, loads are just half the story. Is if you got a load, it means the beam is moving. So you need some sort of support to resist these actions. And there's also a number of different supports that you can play with. So we either have a pin support, is a single pin, and as the name suggests, it allows for rotation. So you can rotate it up and down, left and right, depending on how many axes is actually pinned on, but it won't allow for those vertical forces or those horizontal forces. As you can see, it's a triangular shape. It's stopping both the vertical translation and the horizontal translation. Along the similar lines of something that's a little bit less restrictive, and this is a roller, and it's normally displayed as a circle. So what type of restraints does a roller have? So a roller allows you to translate left to right, as it can roll on that circle, but it doesn't allow you to have vertical translation. But it does still allow you to be free in the moment, so it can rotate in the moment direction. So as opposed to the pin, which you can't move left to right, it stops translation left to right and up and down. A roller only stops translation up and down. There is one more, which is a fixed support. As the name suggests, it's completely rigid. So you'll see these typically as cantilevers. So it doesn't allow you to move up and down, it doesn't allow you to move left and right, and it doesn't allow you to rotate. So you can have cantilevers on a fixed support situation. So let's start with the three types of forces that you may see on your structure. You actually got three types as well. So you got an axial force, bending force, and a shear force. So what do these actually represent? The basic one is the axial force. This is just a force normal to the face of the beam. So you're either pushing it or pulling it, but the force is normal to the cross section that you're looking at. This is where you're either compressing or pulling it out in tension. Then if we move to a bending force is still normal to the face, but because it bends down, you have a variable distribution normal to the face. So while the top may be in compression, the bottom could be in tension, but the load is still normal to the face of the beam. So it means there is a force that's pushing different from the top to the bottom. So it's variable, and typically you'll see that either bending up or bending down, depending on which way you're seeing those reaction forces behaving. Well, how about a shear force? Well, shear force is slightly different. You see, the shear force is perpendicular to the face, so it's running up and down the page. This is quite often where you'll see a shearing action where the plates are trying to shear across each other. And a lot of time you'll see that stress on a 45-degree angle as well. This is where you get those shear cracks. But a shear force is typically perpendicular to the face. So there are three types of forces and how they impart stress on our structure. Which is one more thing that we need to cover. We need to cover sign conventions to make sure that we're drawing them correctly. So when we're talking about bending moment diagrams, there's one sign convention that I like to follow, where you have the positive is when you're getting a hogging moment. So the force of it bending up and over the top, meaning the top of the beam is on tension. You typically see these at continuous supports. So you've got a continuous support, you've got a hogging moment that goes up and over the top. So you've got the tension side positive. So you can see which side is the positive side. And at the top of the beam is where the tension force is applied. Then you come across and you go below the beam and you've got a sagging moment. This is a negative force, and typically you'll see the bottom of the beam is in tension. So this is a really simple way, especially if you're looking at concrete structures, about where your reinforcement needs to go. Because in concrete structures, you should reinforce the tension face. So by just looking at the bending moment diagram in this way, you know where the reinforcement needs to be. How about shear forces? Well, shear forces are slightly different because it depends on which way you're looking for. If you're looking to the left, you maintain the sign convention. So if the reaction is pointing up or resisting up, it will go up. Or if you look to the right, it should be inversed. So when the reaction that's pointing up under a gravity situation, trying to stop it, you'll inverse it and go down. That's just one sign convention that you need to watch out for when you're looking at shear forces. I'd just like to give a quick shout out to one of my sponsors, SkySieve, who've actually come out with a new tool. So while they still have their FEA software that's very powerful, they've built this new tool that gives you over 50 plus calculators, from IBC to Canadian code, Australian standards and Eurocode. They've even got a broad range from aluminium assessment to scaffolding to timber to steel, so you can assess quickly and easily for any of your needs. They've also built it out in a way so that you can build your own tools. So whether you're just an engineer trying to look to automate, or a manufacturer that wants to have a custom tool that allows you to assess your structure the way you want, it's easily built up in SkySieve. What are they actually offering here? There's actually two ways that you can do this. So you can either buy it as a standalone module if you don't need the FEA software, or you can also have it integrated with SkySieve Structural 3D. But they're actually offering something special to my viewers. If you use the link in the below description, you'll get a 30-day free trial, which is extended to beyond the traditional 14-day one. So you can try it out and see the benefits of using it. You'll also get access to the integrated version with SkySieve Structural 3D, so you can try their powerful new FEA software that's really pushing the boundaries of engineering. I hope you check it out, as it's a really great software. Now let's get back to the content. Biggest thing about looking at bending moments and shear force diagram is remembering your equilibrium equation. Because if you're not in equilibrium, the structure is definitely moving. So there's actually 3 types of equilibrium equations that we need to satisfy. We need to sum all the forces in the horizontal direction to make sure they sum up to 0. You need to sum all the forces in the vertical direction to make sure they sum up to 0. And you're going to make sure that all the moments also sum up to 0. And that's from every section along the beam. So let's start off by drawing some free body diagrams. So we'll draw a simply supported beam, as this will be really easy to derive the stresses, but all these same principles still apply. So on one end, we'll have a pin, which, remember, that just stops the translation in the vertical and horizontal direction. On the other side, we'll have a roller. So that only stops the vertical direction, but allows for the sliding in the horizontal direction. And a beam between. We'll also apply a vertical point load in the middle of it. And for this simple equation, on one side, we'll have a variable description of how to assess the bending moment diagram. On the other side, we'll actually have a worked example. So you can see both how to do it from a variable sense and how to do it from the actual numbers that actually come out of the diagram. We'll just start off with the horizontal one. We're looking at the loads. There's no horizontal loads here, but how about the supports? Could they impart a tension force? On one side, it stops the translation in one direction, so potentially that side does. But the other side is a roller. It doesn't allow for that because it's just free. So we can automatically satisfy that horizontal direction. That's something that's a big tip, especially if you're doing FEA. If you have a pin and a pin, they'll be rigidly restrained. So even if you've got the vertical load in the middle, as it sags down, as the beam tries to elongate, it will pull it out really tight. So there'll be a tension force engaged. So if you're over constrained because you have 2 pins, you will see that you'll have tension forces or axial forces applied, meaning that you won't potentially satisfy that equation without having a horizontal stress in the beam. But in our case, we're lucky, we've got a pin and a roller. So all the horizontal stresses sum up to 0. But there's something that's really missing here, and that's how to derive the reaction. So we've got the point load in the middle, but how do we know what the reaction is on RA and at RB? Well, it's really simple. There's one simple equation that we can use to do this, and that is to sum up the bending moments from any single point. So let's start around RB and try and find out what the bending moment needs to be to satisfy to 0. We're looking to our right. On one side, we can see the point load. On the other side, we can see the reaction. So what does the reaction need to be to sum this reaction to 0? And that's really easy. As we know that the point load is in the middle, which is just L on 2. We've got load of P. So P L on 2 must equal RA times L. Now that we know L and we're trying to solve for RA, we just bring the L onto the other side. In this case, because it's in the middle, we can cross out the 2 L's and we just get P on 2. But if they weren't equal, we'd also still have the same reaction, as we know the lengths of them, and it'd potentially be a fraction of the load depending on where it's applied. But in our case, it's just P on 2. And with the load, with our work example being 30 kilonewtons, means that we just have a 15 kilonewton reaction force. But how about the other side? We've got one more equilibrium equation that we can use to satisfy the other side of this diagram. And that is, we need to make sure the sum of all the vertical loads sum up to 0. So we need to make sure that 0, P minus RA minus RB is equal to 0. Well, in this case, we know that RA is, we know what P is. So we're 30 minus 15 equals 15. We could have just done it the other way because we knew there was half on one side. We know there must be half on the other. But if you're slightly off center to one side, you can still work it out because it means that the reduced force means the other side needs to be equate to balance out the equation. So now that we've got the whole beam structure defined, we know what the reaction forces are, we know what the forces in the structure are, we can start to derive our bending moments and shear force diagrams. Now let's start by just taking a section cut through the middle and looking to our left. So what was the rule? Remember, if we look to our left, we maintain the direction the arrow is going. So in this case, because it's pointing up, because it's resisting from gravity, it means that we just draw a line vertically up to 15 kilonewtons. And we can see there's nothing in between that point, as we need to make sure that each slice is maintaining equilibrium. So it means there's no change. So we have a direct straight line up until the point that we're at, which is right through the middle of that point load. Now, because we're at the point load, we can't actually see it yet because this is an infinite point. We don't see it because we're right through the middle of it. But if we move to our right a little bit and look back, now we can see the point load. So we're going across and up from 15. And because it's 30, remember, we're looking to our left, maintaining the same sign convention. So we now go straight down to negative 15. And then if we're looking to our right, we can see there's nothing else affecting us. So it can just be a straight line all the way to the reaction. So if we're looking to our right, when we hit that reaction, what happens? Well, we've got the reaction in the other direction. And because we're looking up, we just move that force back up to 0, maintaining equilibrium. So the whole summation of the shear force diagram sums up to 0. We're starting at 0 and we're ending at 0. Well, how about bending moments? It's really the same aspect here. We'll take that same section cut to the middle and we'll look to our left. What can we see? We can see RA. We know that we're at L on 2, so just RA times L divided by 2. In our case, we know that the beam is 10 meters long and the reaction is 15. So it's 15 times 10 divided by 2. So now we've got a bending moment all the way down from a straight line. Because there's no variability, it's a straight line down to where we are. If we move to our right a little bit more and look to our left again, now we can see the point load again, and we can also see the reaction force. So we've got two forces imparting on it. So what happens? So we've got 3 meters now. So we've got 15 times 3, which is 45 kilonewtons. But now we've got the 30 kilonewtons times a half. So look at that. With summation, we're starting to go back, progressing towards 0. So we're actually going down to 30. So we've hit the peak in the middle. And if we look the other way, we can still derive our bending moment diagram. So we're at 3 meters. There's actually 2 meters left. So 2 times 15. So we're maintaining that 30 kilonewtons. So it doesn't matter which way we look, we're deriving the same force. So we can see the bending moment diagram starts at 0, peaks in the middle, and ends at 0 on the other side. There's a couple of things that we can derive from the shear force diagram now. So we can see something inherent in these diagrams. We can see that where the shear force diagram crosses the 0 point is where the peak moment is. Now, will that always maintain? I think so, but let's find out with something a little bit more complex. So if we're stepping up the complexity, let's move into the same beam. We've still got a pin on one side and a roll on the other, but let's add a uniformly distributed load. To be a little tricky, let's only add it for part of the beam. So let's start by summating up our equilibrium equations to make sure we can define the free body diagram. So we're looking at the vertical loads and the horizontal loads and the bending moments. We'll start with the horizontal again because it's probably the easiest to derive first. So is there any forces in the horizontal direction? The answer is no. So you can see all the forces are vertical, not horizontal. Pin support on the roll side, so it's stopping that translation in the horizontal direction, so maybe. But again, the roller on the other side is allowing us to free flow. So it means that the horizontal equilibrium equation sums up to 0. Now let's move into the bending moment diagrams, which we were looking at before. So when we look to our left, we can see something very strange because we've got a uniformly distributed load. So it's lots of different point loads. So what can we do here? So we can look at the length of it. So we times by the length and we get an equivalent point load. And all we need to do is apply it in the middle of that uniformly distributed load. So now we have something similar to what we had with the point load. So we're looking to our left. We've got that point load from the uniformly distributed load, plus we have RA. So to make sure that equation that we had before, how can we summate this in a variable format? So we look to our left, we can see that the distance from where we are to where the uniformly distributed load starts is X. We also know that the length of that uniformly distributed load is A. So we know that the distance to that point load is X plus A on 2. Because half of A is right where the centroid of where that point load should be. Now a simple equation, so we've calculated P again, and just P times x plus a on 2 should equal to RA times L. So again, we just pull L out the other side and we can summate what RA is equal to. So if we can see what the reaction force for RA is, we can see that it's roughly about 5.85, as it's not in the middle, so we're not getting that half situation like we had before. We've got one other part of the equation. So now we can summate that last equilibrium equation, which is all the vertical loads must summate to 0. So we've got RA, we've got the point load, plus we have RB, but we don't know what RB is. So we know that RB must equal to the equivalent point load of that uniformly distributed load minus RA. In this case, the reaction for RA is actually 9. So we go 9 minus the 5.85, and we get 3.15. So we can see the summation of the shear forces is different between the left and the right because it's not in the center anymore. Just by using those simple equilibrium equations, we're able to get that remainder of that free body diagram. So now let's start to look at how we can derive this bending moment and shear force diagrams. And again, we'll start with shear forces. This time, we'll take the section card just before the start of the uniformly distributed load. But this time, we'll look to our right. So what was the equation? Remember, we've got to look at the force and do the opposite of what that force is. As that force is pushing up at 5.85, we need to go down 5.85, and there's nothing in between us and that reaction, so it's a straight line as there is no change. So we get the straight line of a shear force of 3.15 all the way up to where we're sitting. Now if we move slightly to our left, now we've moved into the uniformly distributed load, and we look back to the same way, we can still see the reaction force, but we can see partial of the uniformly distributed load. So this will have an effect of driving down the shear force diagram at the rate of change of what the shear force is. So it means that we can go across to a straight line and then peak up. So it means that we'll eventually cross the 0 point partway through this uniformly distributed load. And if we keep moving it across and across and across, you can see the shear force keep going up. So now we're above the 0 point up to the point that we hit RA. And at which point we're at the peak shear force, but then we also see RA. So now we drop down to 0. So we can see got this combination of a triangular distributed shear force diagram with a rectangular as well on one side. So as we went into the uniformly distributed load, we can see the rate of change of the shear force was at the uniformly distributed load rate. Now that we've got the shear force diagram, we can move into the bending moment diagram. So let's look at that same point. So we'll go straight through that 3.15. We look to our right, and we can equate what the bending moment is, similar to what we did before. There's something that we can actually do here that's a little bit easier. So we're looking to our right, we can see the force. Something that's also equal to the bending moment that we get at this point is the area under the curve of the shear force diagram. So why we could do it from equilibrium, have a look at what the force is, and look at what bending moment is, we could just look at the area under the curve of the shear force to get the bending moment diagram at this point. So we can just break this down into a rectangular and triangular form when we hit the inflection point of the shear force diagram. So we've got this curved bending moment diagram up until the point that we get to the end of the uniformly distributed load. Then it turns straight back into a straight line. And we can see a couple of things. So we're still maintaining that same thing that we discovered earlier. When we cross the inflection point of the shear force diagram is where the peak moments will occur. And then we can just use simply the area under the curve to derive what the bending moment diagram is. And we can do that at any point as we move across. We just look to our right, and we can see we've got this nice parabolic curve for the bending moment diagram when we're inside the uniformly distributed load. Something you may have noticed is the differential of the bending moment diagram is actually equal to the shear force. So we can either look at the area under the curve, which is the easiest way to do integration, or the rate of change of the bending moment diagram to get what the shear force is. It's something that we can also double check to make sure that we're actually in equilibrium at each point. So when we look at the far side, has the shear forces all summated to 0? So we've gone back to 0. So are we in balance? And the answer is yes. Have we looked at the bending moment diagram, and does it cross the peak of where the inflection point of the shear force diagram is? And the answer is yes. So we can see we're maintaining some simple rules. So from this, we can also derive where the peak bending moments are just by where the shear force diagram crosses, as a couple of double checks. So how about if you combine point loads and uniformly distributed loads onto the same plot? And it's just law of superposition here. So first off, let's break them down into individual components. On one side, we'll pull off the point load. On the other side, we'll pull off the uniformly distributed load. And we can derive them independently of how we just described it before. Then all we need to do is superposition them together. When we're looking at the free body diagram, do all the vertical forces summate to 0. So we're looking at the point load plus the uniformly distributed load. less the reactions? We can see that they do. All the vertical forces sum up to 0. How about the horizontal forces? Well, in this case, it's even easier. As there's no forces in the horizontal direction, and we've got a pin on one side and the roll on the other, it means there's no way of inducing a horizontal reaction. So it means that in equilibrium, all the horizontal forces must summate to 0. I'll link to a video here about the simple rules of thumb of concrete design that will make your designs better, more efficient, and bring you up to the next level. And if you're interested in supporting the channel, there's 2 ways that you can do this. You can either become a YouTube and Patreon member. Without the support of my YouTube and Patreon members, this type of content would not be possible. As always, keep learning, and I'll see you next week. Bye.